Thank you all for coming back. I appreciate it. So today my talk will be about the Nielsen periodic points theory. All right? I'm having a great time so far. I hope you are too. Okay, so fixed point theory is about f of x equal x. And our goal for today is to generalize those Nielsen theory ideas to this situation, f to the n of x, that's the nth iteration. F to the n of x equals x for various n. These are called the periodic points with period n. I'm sure we all know. And when the n is minimal, I'm going to say that x has minimal period n. So when I say x has period n, it doesn't necessarily mean that it's a minimal period. I'm going to say specifically when I'm talking about minimal periods. So if you want to do Nielsen theory in this setting, the first thing that you would think of is a periodic point with period n is a fixed point of the iteration f to the n. And so you can use the Lefschetz number and the Nielsen number of f to the n. And they're already defined. We talked about it yesterday. So they will count at periodic points, and it will be true that the Nielsen number of f to the n is less than or equal to the minimum number of fixed points of maps homotopic to f to the n. And you might temporarily feel like there's nothing more to say about this, but actually this is not quite what we want. This is true, but not quite what we want. Why isn't this good enough? So over the next few minutes I will convince you that that is not what you're looking for. If you're looking for a Nielsen theory for periodic points, it's not really the Nielsen number of the iterates. So here's an example. S1, let's consider as complex numbers of unit length, and the map is going to be the complex conjugate. So you just flip over the circle. In this case, the second iteration is the identity. So f squared is the degree 1 map on S1. And by the formulas that I talked about yesterday, and several other people mentioned, the Lefschetz number is 0, and the Nielsen number is also 0. All right? But the original map is degree -1, so the Nielsen number and the Lefschetz number are 2. And so all maps homotopic to the original map have at least 2 fixed points. And that means automatically they also have 2 periodic points of period 2. They're not minimal period 2, but they are periodic points of period 2. All right. So the Nielsen number of the second iterate is 0, but every map homotopic to f must have at least 2 periodic points of period 2. All right. So something is a little wrong here. If the Nielsen number was 0, then it's, especially on the circle, you should expect it. That means there are no periodic points of period 2. That's not the case, though. All right. Oh, what happened? Well, there's a subtle difference. So the first quantity there is the minimum number that we talked about yesterday. Mf of f squared means the minimum number of fixed points for maps homotopic to f squared. This is not the same as this one here. You see the difference is I am allowing g to be homotopic to f and then looking at the fixed points of g squared. All right. The question is, do you vary the second iteration by homotopies? Or do you vary the original map by homotopy and consider the second iteration of all of those homotopic maps? Really, if you're thinking about Nielsen theory for periodic points, the second one is probably what you want to be talking about. And these are different numbers. All right. In our example, the first one was 0 because the second iterate was the identity map, which can be made fixed point free by homotopy. But the second quantity is greater than or equal to 2. That's because what I said before, any map homotopic to this map has to have at least 2 periodic points of period 2. So those are 2 different numbers. In other words, so the issue is when we look at the iteration, the nth iterate, we should only be changing f by homotopy, not f to the n. All right? And if you just do the classical Nielsen theory, then you will be considering all homotopies of f to the n, which is not what we're interested in. It doesn't give you what you're looking for. All right. There's some more subtleties, some more kind of surprises. How do the fixed point indexes depend on iteration? If you know the index at a particular point, what does this tell you about the index of the iterations? You might think that maybe if the index is some constant, then the index of the next iterate will be that constant to some power or something like that. Turns out actually nothing like that is true. What does this tell us? Not much. If you know one of the indices, actually the other indices you don't have information about the other ones. In our example, the index was 1 on the of the original map because the Nielsen number was not 0, but the index was 0 of the second iteration because the Nielsen number was 0. So it can be 1 and then 0. It can be 0 and then 1. It can the index has a very complicated relationship. So the sequence of the fixed point indices can be fairly unpredictable. And actually, this is even true for the Lefschetz number, which is allegedly a simpler thing. But the sequence of the Lefschetz numbers does not, for instance, obey a simple relationship from one iteration to the next. All right. This was actually studied by Dold, and he has a kind of a nice theorem. So for each n, we have this congruence holds. The mu here is the Mobius function, which is something from number theory. I don't want to get into the details here, but the sum of the Lefschetz numbers of the iterations over some divisors. This exponent here is going to be an integer. This is not a fraction because k is a divisor of n. Anyway, this sum is always equal to 0 modulo n. All right, this seems kind of a strange condition. This is a set of congruences, and this is called the Dold congruences for the Lefschetz number, is what I'm talking about here. It's actually also true for the sequence of fixed point indices if you make sure all your definitions are correct. All right?
Actually, this congruence was known to Gauss.
To Gauss? Okay.
And you can deduce Dold congruences to Gauss congruences for algebraic number.
Uh-huh.
It's a big surprise, nice story.
It surprises me.
It's a surprise.
Just long before elections.
Yes, much longer. All right. Great, thank you. In fact, this is kind of remarkable. Dold actually proved sort of a converse to this. In fact, the Dold congruences are the only restriction on what the sequence of fixed point indices or Lefschetz numbers can be. So if you have any sequence which satisfies the Dold congruences, then there is a self-map of an ENR, which is like a slightly more general than a complex, such that your sequence is the sequence of fixed point indices if you appropriately define what you're talking about.
Like Gauss
No.
knew
Yeah.
He doesn't know Lefschetz number.
Yeah.
Lefschetz number are traces of matrices.
Yes, yeah, for the right.
Level of number Gauss discovers.
Mhm.
I mean, this beautiful.
Yeah, I'll mention that Dold's space, the ENR sometimes in Dold is not compact, and so it's also definitely not always a manifold. So there's, but very interesting, I think. All right, lots more people have worked on this by say restricting. You can get stronger conditions on the sequence of Lefschetz numbers or indices if you, for instance, require your map to be a homeomorphism, or I believe smoothness is important in this also. So there's been a lot of work on congruences like this. And by the way, I should mention, you can also study the asymptotic behavior of the sequence of Lefschetz numbers and the Nielsen numbers. You can use those sequences to define zeta functions, and I believe Gert-Jan is going to be talking about it. Did I say it right? Right. Okay. I don't know how to say your last name, so... you can also, so Zhang defined something called the asymptotic Nielsen number. This is the exponential growth rate of the sequence of Nielsen numbers.
Ivanov.
Ivanov, yeah.
What should
And Gauss, yeah. Right. And Zhang, I believe maybe this is also Ivanov, showed that the asymptotic Nielsen number is actually a lower bound for the topological entropy.
Ivanov, but what should find two-line proof?
Okay. Ivanov did it more difficulty, right?
3 pages.
3 pages. All right. This is interesting as a homotopy invariant lower bound for the topological entropy. So. And I believe someone is going to be talking about the topological entropy. Also, the entropy, of course, is studied by lots of people. So, in summary, the behavior of these sequences, the Lefschetz numbers, the Nielsen numbers, the index, is complicated and interesting. And this is all I'm going to say about it, really. We're going to focus mainly on looking at specific iterations, getting information about specific iterations rather than the entire sequence, not the whole sequence. All right? So the theory is not 85 years old. Apparently it goes back to Gauss. But I was actually going to say it's much more recent. The basics of the Nielsen periodic point theory are sort of completely stated by Zhang in his book. That was based on some unpublished work by Halpern, which I've never seen the Halpern papers, but anyway. Yes, there were some errors that Zhang mostly worked out. So there are two basic invariants in the book by Yezierski and Marzantovich. They call them the Nielsen-Zhang periodic numbers, which I think is a decent thing to call them. There's two of them. One is NPN. This is meant to be a count of the number of periodic points of a certain minimal period. And the other one, NPN, is meant to count the number of periodic points of all period n. All right, not necessarily minimal period. And they're two different things. And they actually, when you see the definitions, they're actually quite different in character from one another. So we're going to discuss the definitions, along with some basic properties and relations between them. We're also going to talk a little bit about Beckon theorems related to these things, and that will be all. For an idea about what kind of properties you should expect, here's an example. For any map, for an individual map, this is always true. The number of points with period n is the sum of the number of points with minimal period k for all divisors of n. All right. So that's true for an individual map. We could hope, perhaps, that we have something like this: the Nielsen, the n phi of n, which is meant to count all points of period n, perhaps is equal to the sum of the np of n's overall. Sorry, this should be k, npk overall divisors k of n. Sorry about that. This actually, such a summation formula is true for some nice spaces. It's not always true though, and we'll talk a little bit about that. So the definitions of these two numbers are a bit subtle. You can hardly blame anybody for writing papers that got the details slightly incorrect. As usual, we're going to use the Reidemeister classes and the fixed point index. These are kind of the standard ingredients to any type of Nielsen theory. But we also need to talk about minimality of the periods. That is the principal difference between these two numbers, the NP and the Nphi. How can you tell if something or other is representing a minimal period or not a minimal period? Well, it turns out you can do this algebraically by looking at the Reidemeister classes. So let's talk a little bit about this. Obviously, for points, for periodic points, there is an inclusion like this. The fixed points of f to the k are included in the fixed points of f to the n when k divides n. All right, every periodic point of degree k of period k is also a periodic point of period n if k divides n. All right. We would like something like this for Reidemeister classes, right? If there's some kind of way to include the lower Reidemeister classes into the upper Reidemeister classes. So, for example, if I have a fixed point which is period k and it has a certain Reidemeister class, this should have brackets around it. Sorry. Then, what is the Reidemeister class if I view x as a periodic point of a higher iteration? All right. A very sort of naive first answer would be, well, wouldn't it be nice if they were the same? It should have the same class if you view it as a lower period, or the same point as viewed as an upper period should have the same class. Well, it can't really be the same because these two sets, these Reidemeister sets, are different sets. Sorry, they're not groups. I have a lot of, sorry about this. They're different sets, right? For example, on the circle, if f is degree d, then the set at the kth iteration is the integers mod 1 minus d to the k, and at the end it's this other one. All right, actually they are groups in this case, but usually not. So you can have the same Reidemeister class from one level to the next in general, but what we would like is some kind of a map, hopefully an injection, although it's not always going to be, which respects the periods. That is to say, well, what I mean by respect the period is if x is periodic of period k, when you consider it as a periodic point of period n, it should naturally, the Reidemeister class should somehow be the same or something like that. It should be according to a map. All right, and there is such a map. Here it is. It's called the boost from level k to level n. So I'm going to write iota kn. It goes from the Reidemeister classes at iteration k up to level n. And this is the definition. So what you do to a class alpha is you multiply alpha times f to the k of alpha, f to the 2k alpha, up to f to the n minus k of alpha, and then you take the class of this in the nth iteration Reidemeister set. These exponents up here are not representing, they're not really exponents. This is just to remind you of which level of iteration I'm talking about. So this alpha is an element of r of f to the k. This thing over here is an element of r f to the n. That's what the n up there means. All right. Okay, the boost does appropriately respect the periods of points. This is what I said we want to be true. So what I mean is, if x is a periodic point of period k and it has a certain Reidemeister class, when we consider the same point as a periodic point of a higher period, it has the class which is the boost of the lower class. All right. The boost also composes nicely. If you want to boost from one level to the next and then again boost from one to the next, then it's the same as so. This is what you want. If m divides k and k divides n, then the boost from m to n is the same as boost from m to k and then k to n. All right. So everything you want to be true is true. All right. So here's a definition. When something is in the image of some boost, then we say that Reidemeister class is reducible. All right. Then the idea is, otherwise you say it's irreducible. So this is the algebraic version of detecting whether something is a minimum period or not. All right. You can, if the class is reducible, then at least hopefully that means that the fixed points that it represents can be written with lower period, and if it's irreducible, that means they have minimum period. That's the idea. All right. So this is good. If we want, we're close to being able to define a Nielsen number for minimum periods. Then, so if we want a Nielsen number for minimum periods, a good idea would be to define it in this way. Just take the number of essential irreducible classes of the Reidemeister classes at the nth iterate. All right, just the ordinary Nielsen number is the number of essential classes. If I want to include only points with the minimum period, perhaps we should just consider the essential irreducible classes. It turns out actually this is still not quite good enough, although this is pretty close. You have to consider the orbits a little bit here. So the periodic points, of course, they live in orbits. And if something has minimal period n, that means the orbit actually contains n points, right? Not fewer than n. That's what I said. The points in the orbit will all be distinct. And all of those points will also have minimal period n, all right? It turns out there are some times when a point in the orbit will have the same Reidemeister class as another point in the orbit, all right? This is possible. Actually, it's possible they all have the same Reidemeister class. So it is possible to have n distinct periodic points with minimal period n, but only one Reidemeister class, which contains all of them. All right. In that case, your Reidemeister set would just have one essential irreducible class. That is, if this is the only orbit. All right. Only one essential irreducible class because all of those points are in the same class, but it has n different points. So if you are only counting the number of irreducible classes, then you're going to miss something, all right? In this case, this hypothetical example is that you have only one irreducible class, but you still have more than 1 point of minimal period. So the number of essential irreducible classes is not a lower bound for the number of points with minimal period n, all right? So you need to be careful about the orbits. That's the moral of this story. Luckily, you can approach the orbits algebraically too, and everything kind of works out nicely with orbits of Reidemeister classes. So for a Reidemeister class, you can define the Reidemeister orbit in the way you would expect. You just do algebraically, you apply the induced map on the fundamental group n times, and you get n things like this. And like I said before, some of these may be the same as each other. Anyway, an orbit is called reducible if one of those classes in the orbit is reducible. and it's called essential. If one of those classes in the orbit is essential, that is, it represents an essential fixed point class of the iterate. And the invariant, so this is the actual definition that I've been teasing you about all along. The actual definition, you take the number of essential irreducible orbits and you multiply by n. The reason you multiply by n is because each orbit is an indication of n points of minimal period n. All right. This gets around the issue that some orbits may not have n classes in them. Okay. Once you show all of this is well defined, so you can show that all of the what I've just said is well defined, then it's not too hard to show that the this number npn of f is a lower bound for the number of periodic points with minimal period n in the homotopy class of f, changing the original map f by homotopy, not the iterate. All right, and this is what you would want to have out of a Nielsen number for points with minimal period n. Okay, let's do a little example. On the circle, as usual, examples are not too hard to do. So on circles and tori also, things are well behaved. This is, I said this yesterday, when f is degree d, then the Rademeister classes are z mod 1 minus d to the n. All right, and all classes are essential. This is because of the Nielsen theory on the circle works this way. It is also true, this is not obvious, but I'm just going to tell you, you should believe me, all Rademeister orbits at level n have n distinct classes. So on the circle, this issue about sometimes the orbit may only have one class in it, this doesn't happen on the circle. All right. So the distinction between the orbits and the n times the number of orbits actually doesn't matter on the circle. So what I just said, the Nielsen number then on the circle is the number of orbits times n, but in the case of the circle, this is equal actually just to the number of essential irreducible classes, which makes the computation a little bit easier. All right. Okay, concrete example. Let's have a degree 4 map on the circle. So let's compute np1 of f. This is the number of irreducible essential classes. All right. Well, at level 1, all classes are irreducible. Irreducible means you can't reduce it to a lower level. Level 1 is the lowest level. So np1 of f, everything is automatically irreducible. So it's just going to be the number of essential classes of R of f. This is just the same as the Nielsen number, which is 3. All right. np1 is always going to be the Nielsen number. np2, okay. In this case, we want to talk about the Rademeister classes at level 2, and this is the group Z mod 15. There are 15 Rademeister classes. All of them are essential. Again, that's just because of what we already know about the circle. Which of them are reducible? Well, in this case, some of them might be reducible. You have to tell what is the image of the boost, right? Of these 15 classes, which of them are in the image of the boost from level 1? And this is not hard to compute, okay? By the definition of the boost, iota 1, 2 of alpha, I'm writing additively, again, because this is a abelian group. Remember, the definition of the boost is you do alpha times f to the k of alpha times f to the 2k of alpha, etc. All right. In this case, k is 2, so you don't have to do very much at all. Alpha plus f of alpha. All right. Well, f is the degree 4 map, so this is really just alpha plus 4 alpha, which is 5 alpha. So what is the image? Well, you could say this boost, which goes from z mod 3 to z mod 15, is multiplication by 5. All right. It's not hard to compute. So which ones are reducible? They are the ones which are multiples of 5. 0, 5, and 10 are reducible. The other 12 are irreducible, right? And so np2 of f is 12. Once you know what you're doing, this is very easy. np3 is similar. I'll just say quickly. In this case, you get z mod 63 is the number of Rademeister classes, 63. The boost is, I'm just going to write it, this is kind of informal. I'm saying the boost represents multiplication by 21. All right. There is no boost from level 2 to level 3. It's only defined when the lower level divides the higher level, so we don't have to consider that. So which ones are reducible? They are the ones in the image of iota 1, 3. That is the multiples of 21. And there are 3 multiples of 21 in z mod 63. And so np of f is 60. You take away the 3 reducible ones. All right. Okay, it's a little bit more interesting, NP4, because there's 2 non-trivial boosts. This is the last one I'm going to do. Anyway, you can compute so I need to see which ones are reducible at level 4. In order to get to level 4, you can boost from level 1 to 4. That's multiplication by 85. The boost from level 2 to 4 is multiplication by 17. All right, so at the 4th level, we have Z mod 255. And the reducible classes are the multiples of 85 and the multiples of 17. Actually, 85 is a multiple of 17, so really it's just the multiples of 17 are reducible, and 255 is 15 times 17. So we have 15 reducible classes. When I tell people that I'm going to go to a math conference, they imagine that this is what the whole talk is going to be about. Multiplying things. They're right for now. All right, 15 reducible classes, so everything else is irreducible. So the number of irreducible classes is 240. All right. This means that any map homotopic to F has at least 240 points of minimal period 4. All right. You can do a similar thing. I'm not going to go through it, but you can do a similar type of computation pretty easily for tori. This sort of a thing was extended to nil manifolds and some solved manifolds by Heath and Keppelman. And it turns out, so what makes this possible, all of these spaces have some very nice properties that allow you to compute in a fairly easy way. So one thing is we repeatedly use the fact that the Reidemeister orbits at level n have distinct classes. That makes things a lot easier. It's also true, at least for tori, that the boosts are always injective. You might have noticed that actually on the circle. The boosts were always multiplication by something, which is injective. In that case, if all you care about is the number of irreducible ones, you can just subtract off the size because you know the boost is injective. You don't have to actually compute the boost maps in some cases. All right. Okay, so that's NP. NP is a little complicated, but it's actually simpler than the other one. So n phi n of F. Well, this is meant to be a lower bound for the minimum number of all periodic points, not just minimal periodic points. All right. Like I said before, the Nielsen number of F to the n is not adequate for this. I'm going to just mention this quickly one more time. The example was a complex conjugation on x1, S1. Right. So the second iteration is the identity, so the Nielsen number was 0. But the Nielsen number of the first iteration is 2, and so all maps homotopic to F have 2 fixed points, and so 2 periodic points. I said this already. Now the issue here, I want to try and think about this example to give us some idea of how we're going to make a good definition here. The issue, you could say, is that there are 2 points of period 2, there must be, and they are in an inessential class at the second iteration, but they come from a fixed point which is in an essential class at the first level. So we have periodic points at the second level, which in the second level are inessential, but they come from an essential point at the first level. And that's sort of what confuses the issue if you're just using the Nielsen number. All right, I'm going to use this language. They're preceded by an essential class. That means they come from a boost. All right. So really, what we need to count those preceding classes as if they were essential when we want to define this full Nielsen number. Right. Not only the level that we're looking at, level n, we need to look back at the previous levels and also count them as being essential at the nth level. So in order to make a good definition here, given a Reidemeister orbit at level n, this is what I just said, we need to consider all possible reductions into the lower levels to see if it is ever preceded by an essential orbit from a lower level. All right, and if it is, then we need to make sure our invariant counts the lower levels also. Because each such preceding orbit should contribute to n phi of n. All right. Specifically, if you have a preceding essential orbit at level k, you should increase n phi n by k. That's because this would represent k more fixed points. All right. K more periodic points. Okay, so let's get a little specific about this. We need to look at the entire union. This is the Reidemeister orbits. So if you're considering the periodic points of period n, you need to look back at all of the previous levels, which divide n. Those are the only ones you care about. Consider all of those orbits. And a set of orbits at various different levels. A set of orbits is called a preceding system. This is also sometimes called a system of representatives. I like the word preceding, though. A preceding n system, when every essential orbit of the union up there reduces to something in G. So you consider all of the orbits and you want to know what do they all reduce down to. So a preceding system is a single set of orbits which everything else reduces to. All right? If you're thinking about this reduction, every orbit you could say has a depth. That is how far down it reduces, the lowest level to which it reduces. And G is called a minimal preceding system if the sum of the depths is minimal. That's going to be important. All right. So this is the definition now. N phi n of f is defined as the sum of the depths of any minimal preceding n system. All right. Remember what I said before. In this case, if you do it this way, any preceding orbit at level k will contribute k to the sum. Will increase the sum by k, right? And that's actually exactly what I said it should do a few minutes ago. That's what we wanted to do. All right. Pretty complicated, I think. It's a remarkable definition. You know, this is the result of several people struggling, trying to come up with the proper invariant. No, just Boju?
Yeah.
Well, Halpern tried, right?
And it failed.
And failed. Well, yeah, I mean, several people failing to do it.
Okay.
Yes, I don't mean to say that Boju had a lot of help on this. Yeah, a lot of people wrestled with this. Boju triumphed. Right? It's pretty complicated. I think it's a good definition. The definition being so complicated, if you're lucky, you can compute it by other means. It's actually kind of a pain to compute using the definition. Hopefully, some other things will help you out. For example, this one, which I mentioned about a half hour ago. When can you write the n phi n as a sum of the npk's? Let's talk about this. So the quantity on the left, remember, is the sum of the depths of a minimal preceding system. I would like to relate the minimal preceding system to the total number of all essential irreducible orbits. That's the thing on the right. Remember, npk means the number of essential irreducible orbits times k. All right? So any preceding n system, let's think about this, it must contain any essential irreducible orbit. The preceding n system should be a set of orbits to which everything reduces. But if one of your orbits is irreducible, it doesn't reduce to anything else, so that must be included in your preceding system. All right? So any essential irreducible orbit at level k, in fact, is part of the preceding system, and the depth is k. The depth is the lowest level to which it reduces. If it's irreducible, then the depth is k. All right? And so the number of things in the preceding system, it must include at least all of the essential irreducible orbits. All right? And if you want to compute the Nielsen number n phi, using that, you should multiply each time by the depth. And so that's why I have multiplication by k there. The number of essential irreducible orbits in R f to the k times k. But that actually is np, right? That's the definition of np. So what that means, n phi n is always greater than or equal to the sum on the right there. So half of this equality that I wanted is automatically true. The other half is not true. So it's not always true that they're the same. But the n phi n is always greater than the sum. All right. Here's a counterexample. Consider the antipodal map on S2. So in this case, S2 is simply connected. So the Reidemeister sets are always there's one Reidemeister class at every level, since pi 1 is trivial. So all the classes at every level reduces to level 1. The iota, the boost, is just the identity map every time. Everything reduces all the way down to the bottom level. But the level 1 class is inessential. I'm talking about the antipodal map on the sphere on S2 is fixed point free. So the Nielsen class at the bottom level is not essential. All right? So in this case, we have Rademacher classes at every level. They are all reducible, and they all reduce to the bottom level, which is inessential. All right. All classes reduce except the bottom one, which is inessential. All right. The even level classes are essential. That's not really important. So that means there are no essential irreducible classes, right? All the upper level classes reduce, so they're not irreducible. The bottom one is irreducible, but it's not essential. So on the whole, there are no essential irreducible classes, and so the NPN is always 0 for all n, I should say. But f squared, I'm talking about the antipodal map, f squared is the identity, and so the Nielsen number of the second iterate is 1, which means there must be periodic points in period 2. So any preceding system contains the class at level 1. Yeah, so we do have an essential class at level 2. And so a preceding system must include the bottom level so that you can capture the boost from the second level. That means n phi n is 1. The minimum system is just the class at the bottom level. But the sum of the NPKs is 0 because each of the NPKs individually is 0. All right? So this is a counterexample to the summation formula. The issue here is that we had an essential class at level 2, which reduced down to an inessential class at the bottom. If that's the reason why this example had this issue. In that case, such a class is going to be counted in the n phi of f, but it's not counted in any of the NPs. If you want the sum to work, then you just have to require that that never happens, what I said at the top. So the name for this is essentially reducible. You say f is essentially reducible. It means the reduction of any essential class is also essential. That is not the case for the example that I just talked about. All right? And there's a theorem about this, Heath and you. If f is essentially reducible, then you actually have the equality. And it's not difficult to show this. In that case, the n phi n is actually much easier to compute. You could just compute the NPs, which generally speaking are simpler kind of thing to compute. The essential reducibility holds for maps on tori and all nil and solved manifolds. So this isn't a terribly obscure feature. It really does hold, at least for the typical usual Nielsen theory example spaces. All right. So for nice spaces, you can compute the n phi in terms of the NPs. All right. Actually, if you think a little bit about this, it seems like maybe you could do the other way around also. It seems reasonable you could compute the NPN in terms of the lower n phis by some kind of inclusion-exclusion. Here's what I'm getting at here. For example, the number of P6, that means the points of minimal period. The points of minimal period 6 of a map, well, to find that, you could consider all points of period 6 and then subtract away the points of period 3. Subtract also the points of period 2. If you do those two subtractions, you will have subtracted the points of period 1 twice, so you add them back in. This is a typical inclusion-exclusion kind of a thing. If this kind of a thing would work for the Nielsen numbers, then you would be able to compute the NP in terms of the n phis, all right? You include or exclude based on how exactly the levels are dividing into one another. We excluded the 3 and the 2 because they divide into 6 the one time, but you have to add back in the 1 because it also divides the 2 and the 3. And it actually does work if you assume essential reducibility. It's the same condition that I said before. And this is the theorem. If f is essentially reducible, then NPN of f is equal to the sum of something, something, something involving the lower n phis. And this minus 1 to something is the inclusion or exclusion. And I don't want to really get into the something, something, but it's about the divisors of n and how exactly, which level you're taking, how exactly does it divide into n. It tells you if you should be including or excluding. All right? It does work if the thing is essentially reducible. Actually, if you know about Mobius inversion, this is kind of a combinatorial trick that you can do. If you have any sum, anything which is equal to the sum over all divisors of something else, you can always kind of turn the tables and write the summation the other way around with this kind of inclusion-exclusion thing here. So if you like, you can just say, you do Mobius inversion on the other formula, and you get this one for free. All right? Several other identities that are based on stronger types of reducibility. What I've talked about, essential reducibility, there are several strengthenings of that, which I'm not going to talk much about. Sometimes even you can express the n phi in terms of actually the Nielsen numbers, just the plain Nielsen numbers. This is a great situation because they're a lot easier to work with. In particular, there are formulas like this for tori. Okay, let's talk about Beckon theorems. I have about 5 minutes, 10 minutes left, something like that. So let's talk about, the question is it really true that n phi n is really the minimum number of periodic points in period n that you can get? All right, this is a big question, and a similar question for npn. Is this really the minimum number of points at minimal period n that you can get by homotopies? As usual, probably we have to assume, definitely we'll have to assume that we are not in a surface, all right? Manifolds of dimension not 2. Here's a theorem that we would like for n phi of n. If x is a manifold of dimension not equal to 2 and f is a self-map, then there's some map such that the n phi n is equal to, this is not what I mean. I mean the minimum number. No, this is what I mean. Yeah, I should have written it differently. Anyway, you know what I'm talking about, the Beckon theorem. This was stated by Halpern, assuming that the dimension was greater than or equal to 5. This was sort of his conjecture that this would be true if your dimension was 5. And this was called for some time the Halpern conjecture. And it was fairly recently proved by Jezierski for PL manifolds. First he did dimension greater than or equal to 4, and then in a later paper, greater than or equal to 3. And I think the second argument is actually simpler. Yeah, it's a better proof that works in dimension 3. All right. In fact, this is one case in which it's a different story. If you want to realize the minimum number by a smooth map, there are some different things happen. So he's going to talk later today about that. Something to look forward to. What about the npn of f? What we would like to say is this, and I think I said the same kind of a way. We want a Beckon theorem for the least, or the points of minimal period n. And this is also true. I think I asked Jörg about this yesterday, and he thought for several minutes and then said, yes, it must be true. So take that. I believe him. This is not mentioned in his other papers about it, though, so I'm not actually sure. You could ask a slightly stronger Beckon property would be like this. If x is a manifold, again, dimension not a surface, and a self-map, is there some specific map which realizes the Nielsen numbers for all iterations? All right. So what I said before was, if you choose a specific level of iteration, can you prove the Beckon theorem, find a map that realizes the Nielsen number? The answer is yes. What about if you want a single map which realizes the Nielsen number at all levels of iteration? This, I'm going to call this a simultaneous Beckon theorem. All right? And you could ask a similar question for the n piece. Okay? For n phi n, this is an open question. All right? Again, I asked Jörg about this just to make sure. And I think it's not hard to do for any finite number of periods simultaneously. But if you want all of them, you'll have problems. It's a hard thing. What about npn? In fact, it's not hard to find examples that show it's not possible to do simultaneously, even for two different periods. Here's an example. The antipodal map on S2. So if you recall, all the np's equals 0. The npn of f equals 0 for all n. We already talked about that. So if you had a simultaneous Beckon theorem, it would mean you could change the map so that it has no periodic points of any period. But that's not possible because at the second level, the Nielsen number equals 1. And so there must be, no matter what you do, there must be some periodic points of period 2. They could be minimal period 2 or they could be minimal period 1. But you can't remove all minimal periods simultaneously. So that's what I said. You cannot. So the simultaneous Beckon theorem for NP is not true. All right. Next time I'm going to talk about coincidence points. So I hope you'll still be interested. Thanks.